Okay, welcome back. As usual, if you have any questions about the current status of the compiler, feel free to ask them in the chat, but let's recap what we did last time. So the current status of the compiler is we're able to parse expressions that involve constants only. And then we're able to parse them, generate code for them, and execute them. So here I've got a very simple thing that just does something, and the result is 7. When executed, because 1 is 2, so we take the first branch, and 1 plus 2 times 3 is 7. This is done by carefully evaluating each expression in turn, keeping track of the order they need on pushing the operands onto the stack. And as we can actually see here in the generated bytecode, it directly pushes 7 onto the stack, because everything has been constant folded away. It only involves constants, integer literals, so everything can be constant folded by allow when we generate the bytecode. So we're going to change that this time by adding variables, so that we actually have like dynamic values that we're actually doing something interesting and not something that can be constant folded away. But before we can actually start implementing variables, we have a bit of technical debt that we need to clean up in the parsing code, because the way we're currently parsing declarations, function declarations, is completely wrong. It's just hard-coded for the simple case and doesn't work for the general grammar. Because parsing declarations in C is a bit tricky. They've got this nice, elegant system where the declaration mirrors how you would add the expression. But this means that parsing declaration also involves parsing a subset of expressions, which makes it a bit annoying. So the grammar for declarations is a bit complicated. Like this is all just to parse a single declaration. All those pages just parses something like int I. So I've extracted the for us relevant parts of the grammar. So a declaration. Declaration consists of a list of declaration specifiers. And declaration specifiers consist of two things. We've got things like extern or static, so like the qualifiers you can put on a declaration. And then we've got the type, but not the real type, only the core underlying type that happens when you strip away all the pointer qualifications and array qualifications and function types and so on. So like the very underlying type of a variable. So for example, a declaration specifier can be something like int, and specifies that the real underlying type, if you keep dereference it and array accessing it, you will end up with an int. So that's the declaration specifier. So we start with a list of declaration specifiers. And then we've got an init declarator list, which is just a comma-separated list of declarators and optional initializers. And the declarator is the actual thing that defines a name. So at its very core, a declarator can be a direct declarator, which can be an identifier. So a declaration can be something like int I, in which case the specifier list consists of int, and I is our declarator. So we declare an int called I. We can then also declare multiples using commas, so j and k. But we can also have more complex declarators. For example, we can have a pointer. I haven't shown the grammar, but we can do something like star pointer, and now we're declaring pointer to an int. And this is only this is a pointer, and the rest are still integers, because the star isn't actually part of the type. It is part of the declarator grammar. But we can also declare functions. So a declarator can be a function declarator, which is just another declarator and a parameter list. So we can do something like f. And now we've also declared a function that returns an int, just in the same line as we did all the other variables. This function can take parameters. We're ignoring them for now. But crucially, we would also be able to do something like this. And let me remove all the other stuff here, because a function declarator is a direct declarator, which can be another function declarator again. And we can use parents to emphasize this. So we can do something like this in the grammar, which would be, well, what would this be? This would be something called f. It will eventually give us an int, and it is a function, and it also returns a function. So this would be a function that we can call with no arguments, and it returns a function that returns an int. This is syntactically valid, but semantically valid, an error, because a function cannot return a function type. what we need to do is return a pointer to a function. So we would need something like this. And now we've got a function f that returns a pointer to a function that takes no arguments and returns int, and so on. And this entire mess of a grammar is something that we now need to pass. So I've currently hard-coded this type name function thing, and we need to properly implement the entire declarator business. So the first thing is, let's no longer call this type, because we're not really passing a type. We will never pass something called, we will never pass a pointer at this point, because this is part of the declarator. So instead of passing a type, let's pass a type specifier. Just to make this more correctly, only like int can be type specifiers, or like a struct name can be a type specifier, but not something like a pointer to an int. This is not a type specifier. And then we need to pass a list of declaration specifiers. In our case, we're currently only having type specifiers, so a list of type specifiers, followed by like a list of declarators. So let's define a grammar for declarator. But first, we also need to define like some storage to store the data structure, some data structure to store a declarator in. And as you can see, this is also some sort of like recursive nested thing where we can have parents and like the declarators containing other declarators. So essentially we need to define like an entire mini tree language for declarators. So just like the AST, we're going to define like another node hierarchy for declarators. This can be done locally in the translation unit because it's not part of the AST that's exposed to the user. It's only a temporary thing that we create during parsing. So a declarator, we essentially need to copy what we did over here. So we've got an enum declarator kind. Currently we're only having like a name or a function declarator. And then we're having a declarator. It's a node, tree, and a name declarator. This is the way it's called. Yeah, like yeah, name declarator. It's a basic node with declarator kind name. We can use the default base, and this then has like what's it called? S symbol. Node constructor for name declarator. Why does the field have an incomplete type? Okay, name declarator, and then we're having a function declarator. Function, and this can also contain multiple declarators as children, because a function declarator contains another direct declarator as its child. So this is something that we also need to keep in mind. Node zeta for the function declarator. And then we have, let's better. So we take the node constructor tag and then another declarator node. Is our child, pass this to the base. What's the type they've got? Node base. And then insert child after. This is now our child. And then we also need something to get the child. Type is declarator. Its name is the child, and it doesn't have a previous child. So this just generates a getter function by just getting the first child. And also, let's write a constructor for name declarator that simply takes the name directly. node base constructor name. Oh, as symbol. Okay. So those are the two declarators that we can support. Let's write grammar that parses a declarator. And if you can look at the grammar, this mirrors expressions, which is by design. So it also makes sense to parse them as we're using Lexi's expression parsing. So is a Lexi expression production. The atom is either a name or a parenthesized declarator. And then the function declarator, this is sort of essentially like a postfix operator. So we've got a postfix operator that takes parameters. So function declarator, postfix operator. The operator is just open paren, close paren, because we don't actually have parameters at the moment. And the operand is an atomic. And then we start parsing using function declarator. And when we construct a value, we essentially do something very similar to what we did over here. So we return a pointer to a declarator. When we already have one, in the case of parenthesized one, we return it directly because we don't need to express parents in the parse tree. This is of course not name, this is called atom. If we get an atom, we get like an S symbol. Name, in this case, we need to create a new name declarator initialized by that name. And then we're currently only having one recursive one. So we know what this one is. This is a function declarator. It takes a charge. Okay. So this parses declarators. We should still compile. Oh. What are you? Oh, that's a bit annoying. So the issue here is that we are creating it in the AST, but the AST is of a different type. So it contains AST nodes, and we don't have AST nodes. We have declarator nodes. So we need to create a separate temporary tree for that. So this is the declarator tree. And then we're also having a mutable triad tree, triad declarator kinds. Let's call it the decal tree. And this is not triad, this is zero. And then when we pass a declarator, we create all of those nodes in the decal tree instead of the AST. Okay, we're not using it, so but that's fine. Okay, so a declaration now consists of the specifiers followed by a list of declarators. So let's pass a list of declarators. declarator list. We don't have any initializers at the moment, so we ignore those. List of declarator separated by comma. And let's just construct the split vector of them. Declarator pointed to declarator. Okay, so this is our list of declarators. So we pass a single type specifier because that's all we have, followed by a list of declarators, and this is then a declaration. So a declaration passes a type specifier followed by declarator list. And to get the value, we return decl. Then we've got a type and a list of declarators. Standard vector, single declarator. For those decals. Okay. And then we need to add a new declaration for every declarator that we encountered. So in fact, this doesn't actually return anything. All it does is add side effects, which is a bit annoying. Yeah, so let's just make this one not return anything and worry about that later. So we go ahead over every decal that we have. And then we visit it. So we've got two cases. So we can either visit a name declarator, in which case we would create a local variable. Or we would visit a function declarator, in which case we want child. The kind should not be another function declarator. It should be as an atomic node in itself, because function cannot return function types. So this should be the function. Let me write this properly. So the child should be has node has kind. Name declarator. Node by cast name declarator fn. So if it's a name, then we create a new function declaration. Function declaration. Else generate error. Function cannot return function. Okay. So this is a bit, let's implement those as we get there. And then note that this entire grammar does not allow for function bodies. This is because we cannot only use this to declare functions, this grammar, we cannot use it to define functions. Because this is something that can happen, for example, at the local scope, and we cannot define a function in a local scope. So instead, the actual grammar for translation unit consists of external declarations, which is either a function definition or one of those declarations. So we need a grammar rule to pass a function definition, which is we ignore attributes, specifiers, declarator, body. So this means that this one doesn't actually pass a function declaration, it passes a function definition. So let's name it accordingly. And the syntax is type specifier followed by declarator. Declarator followed by name. It means that we get a type and then we get a declarator. And we want that this one must be so this must be a function declarator because we want to define a function, so we need to have declared one. Let's see the function declarator of our decal, which must have a name as its child. Child, which means that we can create a function using that name. Call this one name. Otherwise, generate error, not a function definition, and then return that. Static function declare. Okay, and I've just noticed the typo here. This must be name. The child. Okay, so this now passes a function definition, and then the translation unit consists currently only of function definition. Declarator. The grammar, we need to define that this is an operator. And then we've got an ambiguous call. Because we could pass this one. Obviously. So this one is a bit, so let's define a tag, function declarator, and say that this one takes a tag. I did not overlap this one. Is that a thing? No? Okay. My language server killed itself again. So function declarator from the grammar. What exactly? So this creates an op for tag. Do I have find something? I don't. That's a bit annoying. So if this is a tag, oh, I believe I know how to solve this one. So then we get the type directly, I believe. No? Should know how I use my own library. So the tag, we get the tag type. Oh, I know. Because this is a postfix operator, it comes after. And we are still not actually using this one because we never pass a declaration. So let's worry about that later. Okay, but we still compile. But now we properly pass function definition using the declarator syntax, which means that we could do something like, for example, we can parenthesize the function name. This is syntactically valid. I don't see why you would do that, but we support it because we properly pass declarators and not just names. We can also now trigger like a couple of those to-dos by adding another set of parents here. As you see, the language already says that function cannot return function type. And what we are currently saying is to-do generate error, not a function definition, and then we crash, which is less user-friendly in some sort of way. Do we want to generate nice error? Let's generate nice errors later. Okay. But this is function definition parsing. So now we also need to parse declarations at some point. So let's write something called a declaration statement. So, in fact, I believe I'm missing a semicolon in the grammar as well. So declaration ends with a semicolon. Does an external declaration also end one? No, it does not. Okay, which, yeah, function definition does not end. So at this point, we also need the semicolon. Which means that we can now say that a declaration, that a statement can also be a declaration statement, which is used to define local variables. Right? It's a statement that declares things. And so value decl statement decl statement decl statement. We of course need to define a decl statement. So this is a new kind of statement. Statements that declares something, e.g. int I. Decl statement, decl statement, decl statement, decl, decl, and decl. And then we've got the decl here and the decl there. We haven't declared them, so let's forward declare this. And you really want to so we need to define this here once it actually knows that declaration inherits from node. Yep, I did that. Explicit cannot be specified, fine. All right, decl statement. With an expression anywhere else, so let's just keep this one, don't need to print anything for those. And then we are missing no from decl statement, so seal of decl for second argument. So we're creating, oh, this of course doesn't take a decl statement, takes a decl. And now we need to pass this one accordingly. And this is where it gets a bit tricky due to the way Lexi's grammar works. So Lexi will not do automatic backtracking, which means that every time it needs to make a decision, so for example here it needs to decide between a block statement, a built-in statement, or an expression statement. It needs to know when it should try this one. And parsing a decl statement is a bit, so it's a bit tricky to differentiate between an expression statement and a declaration statement in the general case. For example, we could have something like foo a and b a. And if we have something like struct foo and int b, then the first one declares a pointer to foo, and the second one multiplies b and a. So the first one, this is a decl statement, and this is an expression statement. And differentiating between the two requires name lookup. because fundamentally we don't know whether like a star is a multiplication or a pointer. But in our case, in fact, this does not happen in this case because we would need to write struct foo. So this is only an issue once we introduce type defs, which we're not going for a long while for exactly that reason. So we can always distinguish between them until we do that, and then it gets tricky. So, and then I need to say that this one is a branch, so we can check whether something is a declaration by checking whether we have a type specifier. And which macro isn't what you a declaration statement? So a declaration, and this is the issue. A declaration does not give us, currently it does not give us any value. So let's return a vector of the declaration that we've created. So a vector of declarations. Let's return those. And then we need to change the decl statement. So a decl statement can actually declare multiple things, not just a single thing. Multiple. Yeah, let's just call it things. Which means that we don't have this one. Instead, we have declaration declar. So we can just inherit the default constructor, decl statement, and then we want we'll add that later. So s.cpp. Now we're having an add declaration function. So Stila of decl statement, add declaration, and we just insert them out to the prompt. Can we? Yeah, let's worry about that later. So then here we don't take a single declaration, but a list of declarations. To declarations, result, add declaration, decl, return result. Yep. Okay, now we pass them, but as soon as we try to use them, we will trigger the to-dos again. To do, create local variable. To do, generate error, not a function definition. Wait, why? Why are we reaching this code? We're not trying to define a function definition. Oh. This error is still here. To do, create local variable. We're currently doing nothing, which is not valid, but we can also declare a function. Yep, this is correct. This is a function declaration, and that's what I wanted. To do, create function declaration. Okay. Variables. We pass them. We now need to add them. So this requires a new kind of declaration, a variable declaration. Declaration also has a name and a type, does not have a block. Name and type does not have a block. And then later we worry about initializers and things like that. And when we print them, we don't need to print extra data, so we just need to add them. Not here. Here. Variable decl. Variable decl. Okay. And finally, we can add them in our parser. So when we, instead of this to do, create local variable, we instead create a local variable. Which means we now need the state and the type. Var state as create the variable declaration, and the parameter var what was the order, name then type. So name type, and then we add them to our result. And then we add a capture here. And now we are having a declare statement. So this was the test code. We're declaring a variable I of type int, and here we're declaring a variable. I suppose we should probably print its name. Sounds useful. So let's print. Doesn't every declaration has a name? So we can do that. So we've got a variable declaration I of type int. Excellent. And when we go ahead and actually change it, so JK, this should all work. Apparently not. So let's see what's going on there. We want to insert that alt error. Okay. So the issue again here is we're using the single type node multiple times, which is not okay due to the way, because every node, the nodes are intrinsically linked and we can only add them in one intrinsic list at a time. So we need to clone the type, which is annoying, but since we only have int as type, so just create a new int every time. I will probably refactor the entire thing. Let me copy an int creation from somewhere, because we're doing that a bunch of times. I will probably, here we go. I will probably change the way we're dealing with types in general. Currently, they are part of the AST as like separate nodes. But since they're not first-class entities in C, this is not necessary. We can instead just keep primitive data, and then we can don't have this reference semantics and simply just copy the type. So yeah. So now we're creating two declarations I and j. They're here contained in the reverse order. Because we're calling add declaration, which inserts them in the front, because this is a singly linked list and it's easy to add something to the front. We don't know the last one without iterating it. This isn't an issue for now. I believe this could be problematic if we have something like int I, j equals I or something. I don't know whether that is actually legal. It probably is. This might be problematic there, then we need to do something proper here, but for now, let's just ignore that. So we pass variables. That's great. But we are not doing anything for them. So we need to now generate code for local variables. So let's switch over to CodeGen. When we want to visit. So here we're visiting a bunch of things, and one of the things that we need to visit now is a declaration statement. So let's see now, decl statement. This declares a bunch of new names. So we iterate over all children of this node. Let's add an accessor for those. So we want to iterate over the declarations that are declared by this decl statement. We can get the children from the generic node class, and now we just want to downcast them to declaration nodes to make this one more type safe, because we know it's always a declaration node that is the child, and not anything else. So dryad make node range of type decl children begin children dot end, and you're probably going to complain. You're not actually. Nice. Never mind that. So let's iterate over the. Let's call the statement. Let's iterate over the children. In fact, we don't actually need to do that because we will visit. The visit will automatically visit the children. So we don't need to do that at all. We just need to generate code. So when we visit the function declaration, so we ignore function declarations. We're ignoring them because we don't need to generate code when we declare a function within a function. This is just for name lookup. But we do need to do something when we have a variable declaration. In this case, we want to create a new variable. So allow build asm build local build local. So and then we also need to specify its layout. In this case, we want to generate only having type int, so we can just hardcode the layout. So let's just hardcode the layout to the type of int, which is allow layout native layout of this type. So we just ints are 60. So ints are like the primitive types of the love VM. So when you push an int, we push a love runtime value. So we create a variable that can hold love runtime value, and then we don't need to do anything with this for now. And to do something other than int, handle type other than int. And now when we codegen, we create space for ints in the function. So we say we say that we want to do two local allocations, and the first one is of type int. So 8 ints are 64-bit in love, or then our implementation of C ints are 64-bit. So create them here and create them here. This means 8. So the 8 means 8 bytes, 8-byte alignment. So we create them. Which is great. We can now declare local variables and generate code for them. Of course, we can't access them at the moment. But that's enough to commit them. We don't need the grammar anymore. Declare local variables. Variable declarations. Great. Now the first issue that we have is we can do this. We are creating an I 2 times, a variable called I 2 times, and it doesn't generate any error, which is of course bad. We should prevent that. So let's start doing name lookup. So we want a symbol table. And let's create a symbol table for our AST symbol local symbols. How many arguments do we want to take? Symbol table. Right. So this maps love symbols, so names, to declarations. Then when we start parsing a function, we want to reset, clear the local symbol table. So let's do that by a little hack. Function start. This doesn't actually parse anything, but it allows us to specify a callback that will be invoked before we start parsing the body of the function. So in this case, the callback returns void, takes no arguments because we're not producing anything, and all we do is say state, local symbols, we reset it. So we reset the local symbols when we start parsing the function. So this just ensures that we clear it before we start parsing the body of the function. And then when we pass a decl statement, we add the declaration to the list, but we also add it to the symbol table. So state local symbols dot insert or shadow the name and the decl. And I forgot the return type. If there's replace, otherwise returns right. Auto shadowed. If we have a shadowed declaration, then generate error duplicate declaration name. Apparently it doesn't want to trigger this one. So it really doesn't want to trigger this one. Interesting. So let's just print the names out so we see where we're wrong. So this isn't the issue. State local symbol size. Interesting. It appears that there is a bug somewhere in the symbol table implementation. So this is 5. Let me check. Let me check that the ID is correct. Decl name ID. That the string interning actually worked. And there's the issue. The string interning didn't work. So they're supposed to be interned, but they didn't. That's a bit unfortunate. Why aren't they interned properly? So so it still works at this point. So this is main. This is I. And this is also I. So we don't want to rehash. We compute the hash of this thing. I'm supposed to be... I have written tests for this, which didn't catch the issue. So let's add a bunch of debug statements here. So the pointer is main, the pointer is I. We go into the hash table. We compute the hash. Oh, yeah. Now what the issue is. This isn't a bug in Loaf, this is a bug what we are doing. This is a bug in Loaf. Okay, so the issue is that the API takes string and size, but the implementation assumes null terminated strings. So it just ignores the length specifier for lookup, which is obviously an issue because, right, you're supposed to. This is not a null terminated string. So I and I were different because they weren't I, they were I, and then the entire rest of the program, and then everything else. So let's temporarily create a null terminated string. I need to include string and fix the API of Gamma. Now we're actually getting the error where we have a duplicate declaration name. Okay, so let's create a nice error message for that situation. By adding Lexi uses already like a bit of logic to print its error messages, so we just piggyback off that. I need to add the input here. So const Lexi buffer, Lexi UTF-8 encoding input. Compiler state. Diagnostic writer. And then deckel statement. So what we want to do is we want to write a message to standard error. So we want to write an error, and the message is duplicate local declaration. Then we write heading. Right. This isn't the interface. and standard, yeah, duplicate local declaration. Duplicate local declaration. The name is decl name C string, state as symbols, duplicate declaration with that name. Then we write a nice empty line, and then we write an annotation, handle annotations later. What do you take the input and then the compiler state? So we take the inputs, 8 encoding input, pass that to diagnostic, fancy visualization. Okay, and now we've got a nicer error message. So to get this one really nice, we need to associate every declaration with source location, so we can like point to the exact source location, but let's not worry about that. Let's, however, set a flag that we had an error. So decl statement state.error with 2, so that we know that if we have an error, we don't actually continue. So now we generate an error and abort. Nice. Handle multiple declarations. Okay, now we've got variables and we actually want to use them. This means that we need to add a new kind of expression, namely an identifier expression, which evaluates the variable. So identifier expression, type, symbol, and name. And we also want to now where we defer. In fact, we don't need to pass the name. We just pass the declaration directly. Decl. So an identifier expression refers to a declaration. And note that this is not a child because the declaration isn't owned by the identifier expression. It's just a non-owning pointer to it. And when we print the identifier expression, we are simply printing its name. Declaration name C string as symbols. Add a const here. Name, which refers to a declaration. Excellent. So this compiles. Let's parse them. So an identifier expression also simply passes a name. So let's move this one on top. So we pass a name and to get a value, we get the name. We again hardcode the type. But first we look up the local declaration. State local symbols. Look up the name. If you didn't have one, we generate an error. Let's also copy the error code from the decl statement. We will eventually create like proper API to generate errors in a less ad hoc way. Unknown identifier. Then we return. We don't actually. Yeah, let's just return null pointer. That will crash. We will handle that more gracefully later on. That copy type of declaration instead. But we can't copy types. So at the moment, this creates an identifier expression. Type and decl. We're done parsing them, so now we want to also support them. So expression, primary expression is a constant or something parents or an identifier. So let's support identifiers here. Let's see whether we can print I. We can't because we don't generate code for it yet. So let's add them to CodeGen. When we encounter an identifier expression, this then should refer to a local variable. So now we need to look up local variables. For that, we need to create a map. Of pointers to declarations to allow locals. We then, whenever we create a variable, we add them, insert or update we don't need to update, so insert them. And when we encounter an expression, look up expression declaration equal to null pointer turn. Let's assert. Because due to the way C works, by the time we look up an identifier, it will already be declared, because just C works nicely that way, which means that we can just want to push its value onto the stack. So for that, we first need to get the address. Then we want to load the field of the primitive type, so it has only the first field of the primitive type. Like so. This one transported there. And there we go. We print 0. So what we're doing here is we create a local variable with this local alloc. Then we are allocating, loading the value of the variable at offset hex 20. It's offset hex 20 because the stack frame setup is 32 bytes in loaf. So offset 20 is the first variable. Then we're loading this value and then we're printing it. And loaf initializes it to 0, apparently. I haven't actually done anything. Or rather, something has initialized it to 0, so that's the value of the variable that we're printing. So that's nice. And if we are having like want to print j, and we haven't declared j, then we're getting error unknown identifier. Great. So that works. We can now get the value of a variable. Support identifier expressions. Of course, we also want to change variables, otherwise this entire thing would be pointless. So let's support that. And for that, we need a new kind of expression, an assignment expression. So assignment expression. So an assignment expression also has an operator, because we can do like plus equals, not equals, and so on. But for now, let's just support only a single. Let's just call it no operator. So we're just assigning. Then we're having the left expression and the right expression. Need to update the constructor. And the left one is the L value. And the right one is the R value. L value, R value. That's where the name comes from. It's on the left-hand side of an assignment operator. So L value, R value. And we can pass those. This is, again, very much straightforward. We just need to figure out what's the correct precedence for assignment. So expression, we've got assignment all the way, so at the bottom, so right before comma, we've got assignment. This is also a right associative operator. So just like comma and conditional, but unlike the other one. Yeah, it's right associative. So we pass a right associative operator. And the operator is zero. Assignment expression none. And the operand is a conditional. Operand is a conditional, except on the left-hand side where it's only like a unit thing. But I don't need to worry about those in general. This is just does something because a conditional expression cannot be an L value, so it can never semantically appear on the left-hand side. But we still allow it syntactically on the left-hand side. I believe this should be fine. Yeah, let's just do it for now. Don't worry about that if it breaks. Because we need to catch the actual error at a later point. So that. Now I need to create something like this. And again, hard coding the type to be int. Okay. And then we also we cannot assign everything to everything, right? The left-hand side must be an L value. So we cannot do something like 5 equals 4, right? Because 5 is not an L value. So we need to assert that something is an L value. Let's just keep this as a to-do for now. An L value. This means that, so this should now be passed. I forgot to print it. What the hell have I copy pasted? Assignment expression is an assignment expression. And then we also do something here. Okay. So this compiles. Let's insert an assignment call. So this also works, but we again, of course, need to do codegen. So in codegen, we need to handle assignment expressions properly. And because we need to treat L values specially, we also need to use the child visitor again, because we can't get the default behavior. So what we need to do is push the address of the L value onto the stack. Right? We don't want its value, we want its address, so we can store something into that address. And for now, let's just, because the only L value, let's just say the only L value we allow is an identifier expression. I believe in C, assignment itself is also an L value. So we can do something like A equals B equals C. Similar to how in C++ it returns a reference. Let's not worry about that for now. To do only identifier expression as an L value at the moment. And then later we will have pointer dereference and things like that. But don't worry about those for now. So we visit the potential L value. And let's just say this is an identifier expression. ID, and then we want to get its address. So we already did half of that over here. We look up the declaration and then push its address onto the stack. And we don't want to handle everything. Okay, so now we've pushed the address, which means that we now need to, eventually we want to store something. We know that we only having one type, so the type is straightforward, and we store the 0 field. And what's the signature? So value first. Push the value we are assigning onto the stack. So this is just a normal evaluation of the R value. And then we push the address, and then we store the value into address. Why do we have an invalid stack index? Oh, right. Because this is an expression, we also need to get a value. So let's just say that we so an expression evaluates to something, and I'm pretty sure it's an L value. So let's evaluate to the address again. So duplicate the address so we can have it on the stack twice. The address stack is now value address address. We want address value address, and then the store will consume value and address, and we're left with only value. So it just means that we need to put so stack is value address. We want value address. We want address value address. So what we can do is we first roll the value over. So we move the one at stack index 1, which is the value on the very top. And then we duplicate the address, which is now at index 1, to the top. And now we store. We leave the address on the stack. Okay, so we're creating a local variable. We are pushing 42. We are getting the address of 42. We are doing some stack manipulation. We are storing something. We are popping the result because it's an expression statement. We're loading it again. We're printing. We're popping something. We return 0 and we print 42. So we declare variable I. We set it to 42. We print it, and we printed 42. Isn't that great? Let me actually see what happens when I do a nested assignment now. So let's declare I and j, and just say I and j are now also 42. And this, it's nice if it, wait, what is this supposed to do? Not that. So this only sets j to 42. It should set both of them to 42. Which is, because we want to evaluate them in the other way around. So the issue here is that the evaluation order does not match the actual order that we're generating it in. So we first, so what we're doing here is we have an assignment expression whose left hand side is I and his right hand side is j equals. That's that. Maybe assignment is. Let me check CPP reference. Maybe assignment is just left associative. No, it is right associative. So this passes correctly as j equals 42, but then we want to evaluate the result. So evaluate the left-hand side, which then now we want to evaluate the value. Okay, so we duplicate it because we also want to return the value. Like so. Okay. So we first evaluate the right-hand side, which in our case is j equals 42. This will then assign j to 42, and the result of that is the value that is assigned into I. So j equals 42 should result in 42, which is what it's now doing. And then we can also assign I equals 42, and so we print 42 twice. So we don't need to don't want the address on the stack, we want the value. What it previously did, it left the address on the stack, and then it assigned I the address of j, which just so happens to be 0 for some reason. That's a bit, because of some optimism. Okay. So now this one actually works properly. So we can declare local variables, we can assign them, and we can print them. That's what I have planned to do. So let's commit add assignment of variables. There's a bunch of cleanup that we need to do in the long term. There's this bug in the dry symbol internal that I will fix off camera. And then there are a bunch of we've reached the point where we started generating error messages because identifier cannot be found, declared the same variable multiple twice. So we need to create some sort of API for that. We also need to handle types properly at some point. Let's just, I will tackle some of it off camera, some of it in the next stream. But now that we've got variables and actually can start doing more interesting things, next stream, I will add function calls, potentially either parameters or global variables, whatever's easier to implement, probably global variables. So we can sort of declare parameters as global variables. But once we have function calls and local variables, then we can actually start writing interesting programs, just to test them and see what the performance of the VM and things like that. So thank you very much for listening, and until Tuesday.